Welcome to Math 25, talking about probability and odds on Tuesday of week 9. We're talking about three different things, probability and odds, and then also we will talk about ways to measure change as the capstone of this. And that last part is what will really be important for people with certain degrees or programs or majors, so that you are aware when reports of things are exaggerating by using one measure of change or another. But let's start at the beginning. The probability of a situation happening is the ratio of the what we'll call desirable outcomes, the ones we're talking about, the ones that we're counting, to the total possible outcomes. And often in a probability, we will change this ratio into percent format. As an example, here's rolling 2 dice. And let me move over to here. If I roll a 1 and a 1, the sum is 2. If I roll a 3 and a 5, oops, I said 4, 3 and 4, the sum would be 7, and so on. So this is a table of the sum of 2 dice. So the first problem, when you roll 2 dice, what's the probability that the sum is 7? So I'm going to take the green ones, where the sum is 7, and count them. 1, 2, 3, 4, 5, 6. There's 6 ways. So remember our definition. The probability is a ratio of the outcomes we care about, the desired outcomes, the ones we're counting, to the total. So we just counted that there were 1, 2, 3, 4, 5, 6 that were 7s. Those are the ones we care about for this problem. And how many total are there? We have 6 by 6 is 36, or we could count all the squares if we really wanted to. So we get 7 out of 36. I'm sorry, I am counting wrong because I am asleep today. 1, 2, 3, 4, 5, 6 out of 36. Let me fix that. Okay, so if we wanted to, we could change that into a percent, top divided by bottom. So we get 6 divided by 36. That'll be 0.16 repeating. So about 17%. By now in the term, I think I'm going to stop after this, writing that we would do 2 decimal scoots right into percent. You should know this by now. The 6s keep going, so the next 6 would round that one up to a 7. Okay, so this is the things we're doing. I'm going to keep using the word desired, and you'll see why in a moment, instead of the ones we care about. And it's not quite the right word because we actually often have 0 emotional investment in this, or maybe we're even measuring something like how much people get sick and we don't want it to happen. But that's just sort of the traditional way to talk about this. Let's do one more. When rolling 2 dice, what's the probability of the sum being 10? So again, the probability is the desired over the total. The total is still 36. How many squares are in our chart? And how many had a sum of 10? 3 of them. So if we wanted to make a percentage out of that, we could. And we'd get 0.083, which is about 8%. If we want to put a box around our answer, it would make sense to say this is an answer, and it would make sense to say this is an answer. We could write it as a fraction or as a percent. What we probably wouldn't want to do is write it as 1/6. If we reduce this fraction, then yes, 1/6 is a valid way to write 6/36. But there's nothing here about one thing being desired out of 36. This would be counting some other picture. So this is mathematically a legitimate way to say 6/36, but in the topic of probability, it would be kind of awkward to write something that is a real life. We counted this many and we counted this many, and change it to something that's not from real life. Similarly, we could say 3/36 or 8%, but reducing this to 1/12 would be a little weird because there's nothing that here was 1 or 12 that we were counting. Enough of dice. Let's be a little more inventive. There's a gumball machine with equal amounts of 3 colors of gumballs, red and green and blue. And here's a table that has all the possibilities. So we could get this square, a red, and a red. Or this square, the first 2 gumballs are red and then one is green. And this square, 2 reds and your third one is blue. Or this square, the first gumball that comes out is green and then you get 2 reds, and so on. So there's 27 possibilities. 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9 times 3 is 27. So if we get 3 gumballs, how likely is it that at least one of them is blue? So same as before, our probability is the ones we desire. In this case, at least one blue over total. The total we just said was 27. So how many of these have at least one blue? There's a blue. There's at least one, at least one, at least one. Blue, 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 blue. Okay, now let's count those. Oops, I forgot one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 19 out of 27 had at least one blue. If I wanted to write this as a percent, I could. So 19 divided by 27, top divided by bottom, gives me 0.703 repeating. So that's about 70%. Ta-da. So that's the basics of probability. You count 2 things, how many the question is focused on and how many total outcomes there are. Often the biggest amount of work is making the thing that you count, making this list of all the possible outcomes for the gumball machine or for adding up 2 dice. Once you have the list, the problems are easier. The next thing we're going to talk about is odds. The odds of an event and the odds of a situation are the ratio of desirable outcomes to, and be careful, undesirable outcomes. So we're changing only the denominator. And just the way that odds are used socially, we will reduce this ratio, but we won't make it into percent format. So I'm going to take our previous problems and do a compare contrast. So this one, when we rolled 2 dice, and what was the probability of the sum being 7? Now we're going to do the odds, and the formula is different. It still has desired on the top, but the bottom is undesired. So in this case, it still has the 6 green ones. But on the bottom, how many aren't green? We'd have to take the 36, remove the 6 green ones, and have 30 left. So as we said a moment ago, with odds, we could just put a box around this, or we could reduce it, divide top and bottom by 6 and get 1 out of 5. Odds we also might want to write as 6 to 30 with a colon, or 6 to 30 with the word 2, or 1 to 5 with a colon, or 1 to 5 with the word 2. Any of those are also acceptable answers. If odds seems awkward, it's because you don't spend too much time taking SAT tests or betting on horses. Odds are a different thing. It's the desired ones versus undesired. And this is why we switched from cares about to desired, because then we could have the opposite, undesired, as a nice convenient word, instead of trying to, in this denominator, say not cares about or something like that. Okay, continuing. What are the odds of the sum being 10? So we'll go back to our second slide, grab our work. So that was what we did before. Now when we do odds, it still has desired on top, but the bottom is undesired. So the desired ones are 3, those 3 pinks, 1, 2, 3. How many of the 36 are not pink? That would be 33 of them. Take all 36, remove the 3 that were pink, and get 33 left over. So we could write this as 3 over 33. That's great. We could write it, divide top and bottom by 3 as 1 over 11. We could write it as 3 colon 33, or 3 2 33, or 1 colon 11, or 1 2 11. I'm not going to try and put boxes around all of those. It would look messy, but those are all great answers for the odds problem. And you can see what we're going to do next. If we get 3 gumballs from that gumball machine, what are the odds of getting at least 1 blue one? So this is how we did things the first time with probability. And odds is just a little different. So 19 of them had a blue. How many didn't have a blue? You can subtract. You can just count. 1, 2, 3, 4, 5, 6, 7, 8. And there's no common factor to reduce by. So we could write it 19 colon 8, or we could write it 19 to 8 with the word 2. All of those are good ways to write this. So that's odds. Okay, as always, there's some videos about that if that helps you. And now we're getting to the interesting part about measuring change. So imagine there's a medicine that can reduce one of your family members' cancer risk. The chance that someone would have this type of cancer is 44 out of 10,000. And if you take the medicine, your risk goes down to 11 cases out of 10,000. But the medicine does have some bad side effects. You don't want to take it for no reason. So is it a worthwhile medicine? And this is a little tricky. You sometimes have to stare at it. So I've actually done the problems out on the website. We could use subtraction, and this is called an absolute change. The old risk was 44 out of 10,000, so 0.44%, not 44%, just 0.44, less than 1%. Similarly, the new risk is 11 out of 10,000, so 0.11%, not 11%, but less than 1%. These are very small chances. If we subtract them, 0.44 minus 0.11 is 0.33%. So the medication would reduce the risk by 0.33%, a third of a percent. That doesn't sound like very much. And it's not surprising at all that this number is tiny, because if we're taking tiny things and subtracting them, of course the answer is tiny. This way of thinking assumes that we are looking at a huge population of healthy people. Almost no one will get the cancer. So the chance that the medicine actually helps them is small, because going from 44 to 11 would be nice, but almost everybody in the 10,000 people isn't going to get cancer anyway. They're not destined to have that happen. The second definition is a relative change. So absolute change was first, now we're at relative change. Remember the old definition of a percent change, change divided by original. So that measures how much less likely our new risk is. So we take the percent change. The old risk was 0.44%. The new risk is 0.11%. We just subtracted up here. So the change in change divided by original is the 0.33%. So change divided by original. Now we get 0.75, which is 75%. This says the medication makes cancer 75% less likely. That sounds huge, instead of a third of a percent less likely. And the difference is that this scenario, the relative change, is thinking only among those people destined to get cancer, how much will it help? And yes, 75%, 3/4 of those people would have been helped by the medicine and gone down to 11. So this tiny number as an answer was if we look at everybody, whether or not you are destined to get cancer. And this number with the percent change, change divided by original, is if you were destined to get cancer, how much would the medicine have helped you? These are both completely valid. Subtracting is a way to measure the differences between things. Change divided by original is a standard way to do percent change. But notice how big a difference we get in our answer. This is about reporting numbers and sometimes marketing, not whether your math is correct or wrong. The math is correct both times. It's just different ways of measuring either absolute change or relative change. We could also talk about the words as likely. If we did the new risk divided by the old risk, then we'd get 25%. With the medication, the occurrence is only 25% as likely as before. That's the opposite of the 75%, right? The complement out of 100. So the moral of the story is be careful when you hear about changes that are percents. If you aren't sure if it's an absolute change or a relative change, then hearing that a change is a percent doesn't tell you much information at all. Let's look at more examples. So there's a medicine that fights breast cancer in women who already have breast cancer, and it was popularized because of a certain study. There was a control group with 1,700 women, and 34 of them died. The control group means they didn't have any medicine. Then of the group that was treated with the medicine, only 23 out of 1,643 women died. So we have two questions here. One, what percentage of the women in the control group died? So that was, if we want a percent, we'll do part divided by whole. The part is the 34 out of 1,700. 34 divided by 1,700 is 0.02. Actually, why don't I highlight that instead? And then part two, how about if you were in the treated group? So 23 divided by 1,643 is about 0.14, so 1.4%. So far, so good. The medicine works. A smaller percentage died from the cancer. Continuing the previous problem, what's the absolute change? That's the subtraction one. And I put this box here just to remind us of the lecture from a moment ago, but we're not actually using any of this. We're just saying if we subtract, we had 2% minus a 1.4% is 0.6%. And if we want the relative change, then we want change divided by original. The change we just got, 0.6%. What's the original? Is it the 2 or the 1.4? Well, the original is that you haven't had any medicine put in you yet, right? The 2% is the original state of things. So if I have 0.6 divided by 2, I get 0.3. So 30%. Okay, so we're doing, by the way, more problems for you. So the medicine has some dangerous side effects. There were flu-like symptoms, mild heart problems, stroke, severe heart failure. So about how many of the people in the study, if these numbers were accurate for them, suffered stroke or severe heart failure because of the drug? So we could say that's 5% of 1,643. 5% becomes 0.05, of becomes multiply. So about 82. So if you were in charge of publicity for this drug, what type of claim could you truthfully make? You could look at this and say, it's a 30% decrease in risk. And again, the relative change is assuming that you were destined to get this cancer. Then 30% is a big help. Of course, some risk of side effect is worth it. If you were trying to convince a family member not to take the medicine, maybe because they hadn't been diagnosed with cancer yet, then you could say, the absolute change says in the general population, it's only about 0.5% that it would make a difference. That's a lot smaller than these bad side effects. So be careful when you have absolute and relative change. They are tricky, they appear in real life, and don't be gullible. The last topic we have is weighted average. And this is beloved by students who like finding out what they need on the final. So the weighted average measures the average result for a group of things. So there is a game for what to do. And rather than try and read about things, I'm just going to do this. We're going to take the value for each outcome, and we're going to take the percent chance that it's given as a weight. So attendance only has a 10% weight, homework has a 20% weight, and so on. Notice that the weights have to add up to 100%. On the other hand, these scores happen to be written as percents, but they could be points or something else. So if it helps you, just cross out the percent signs. These are just numbers. These are just values, and this is the weight they get. We're going to take each possible outcome, and we're going to multiply them together. And this is different than what we've done earlier in probability, because before we were looking at only one outcome happening. When you roll 2 dice, you get a sum. When you get 3 gumballs, you get a certain color combination. Whereas here, all 5 of these outcomes are happening at the same time. The student, of course, has attendance and homework and midterm 1 and midterm 2 and final. So 90 times 10% would be point. I'm going to make these all decimals so I can do my multiplication nicely. So do my riplop. Okay, 90 times 0.1 would be 0.9. Draw that nicer. Sorry, just 9. 90 times 0.1 is 9. 80 times 0.2 would be a 16. 82 times 0.2 would be 16.4. 84 times 0.2 would be 16.8. 79 times 0.3 would be 23.7. And when I'm done, if I add all these up, then I get 81.9. So the student's overall grade is 81.9. You can't just add up these numbers or add them up and divide by 5 to find the mean, because it's not that kind of average. All of these are not given the same amount of weight. The final exam is worth more. The attendance is worth less. So we multiplied by 0.1, 0.2, 0.3. We got these partial weights, and then we add them together. Whatever label these had, whether they were points or something like that, then that's the label our answer has. So in this case, the thing that we were measuring for each category was a percent. So our answer is a percent. Okay, now let's do the homeworky one. This student is about to take the final. Here's the grades so far. We don't know what this number is. What percent do they need on the final if they want an overall of at least 76% in the class? So we'll do the same game. We'll take each column. We're going to change the percents here into decimals for multiplying. Use our riplop. And we are, for now, going to pretend that these are not percents, because we don't care in this column whether it's inches of rainfall or points on a test or whatever. These are just numbers for each category. Okay, then we're going to multiply across each row. And I can fit it closer right there. So 95 times 0.2 gives me 19. 70 times 0.21 is 14.7. 75 times 0.17 is 12.75. These numbers aren't working out as nice since it's a random problem. 55 times 0.2 is 11. And then there's something here, I don't know what it is. I'm just gonna say it's y. And when I add all of these together, I want all of them to be 76, because that's what the student is aiming for in the class as a minimum. Ah, well now I can see what to do. These numbers, if I add them together, 11 plus 19 plus 14.7 plus 12 gives me 57.45. Then how much more does this need to be to get up to 76? I'll subtract. And get 18.55. So the equation that I'm left with here is that something I don't know, I'm going to call it, oops, just final, times a 0.22 is 18.55. I suppose I should put that up here. So my final score multiplied by 0.22 is equal to this thing, which we just found was 18.55. This we know how to do. Something times something else is this other number. We need to divide both sides by 0.22 to get our unknown by itself. So 18.55 divided by 0.22 giving me about 84%. So this number here would be 84%. If this is 84 or more on their final, then they would get the grade that they are looking for in the class. Because of the way the tests work, this is a lot of work for one problem. So there's a follow-up easy question. The final exam in the previous problem has 41 questions, each worth a point. So if we want to get 84% of 41, right, we need 84% of these 41 right. So 84% is 0.84, of is multiply. And we get, it's 34 point something. We're going to round up because they need that last problem right. So if they get 35 out of the 41, that's their goal. And this is an easier thing so that overall, if I was grading this on a test, you wouldn't have to do quite so much work for a point. So lots of students actually care about this in real life. They are graded in a way that uses weighted averages. And at the start of finals week, they can look up this information and they're wondering, what kind of final do I need to pass the class? And that's the end of the lecture.